So how how far are stars away from us? But actually not stars today, but today we're going to talk about galaxies, a distant galaxy. Oftentimes scientists, they'll say, or astronomers, it's 100 billion light years away. Well, not 100 billion. 100 million light years away. How do they know that? My gosh, you'd think, boy, they're coming up with those numbers out of the sky. Well, not really. We're going to learn how they find properties of galaxies. For example, how far are they away? So let's do that. Okay. How do I find the distance from a galaxy to a galaxy? Okay, we use, the problem we have is that galaxy distances are too far to employ the parallax method. Remember, we talked about the parallax method in a previous way. And the angles are just too small, so it's too hard to do it. So they use a method, what's called the standard candles method. What they do is they look for a Cepheid star. Now, we haven't talked about a Cepheid star, but a Cepheid star is a pulsating star, a star that is kind of, it's bright and then dim and then bright and then dim. And so you look for a Cepheid star in the Milky Way. So here's our sun. And so you try and find a Cepheid star somewhere in the Milky Way, and then they can use parallax to determine the distance between here and here. They call this distance d sub star, the distance from the sun to the Cepheid star in the Milky Way. And then they look for the Cepheid in the other galaxy, okay? And they can look at that through the telescope. And then they use these equations right down here, and we're going to do an example here in just a second. They use these equations and they solve for the answer. It's really not terribly difficult. The G stands for the galaxy, so that is now, and B here stands for the brightness, and D is the distance. Okay, so that's what we do. And so let's do an example. So when we have a mathematical example, what should you do? That's right, you should get out your calculator. So, what happened here? So here we have a problem. A Cepheid variable in a nearby galaxy looks 106 times fainter than an identical galaxy. Now let's identify what our variables are. And before we, actually, let's write the equation first. The equation is B star, that's the star that you know in the Milky Way, divided by our BG, and this is the square root of that. That says square root, is equal to d sub g over d star. Now what do we know? Okay, so the brightness of the star in the Milky Way is 106 times, actually the Cepheid one is the one that's further away, so we're going to call him 1. Keep that in mind. And then we'll say B in the distant galaxy, no, pardon me, B star, that's the Milky Way, is 106. And the one in the galaxy is dimmer, so he's the 1. There we go. All right, and then the distance of the star, that's what we're trying to find out. And the distance, no, I always get this mixed up. The distance of the star is 1,000 parsecs. And the distance to the galaxy, well, we don't know that. We're trying to find that out. Okay? So we're going to use our equation over here. We're going to take these numbers and plug them into the equation. So B star is 106 divided by 1, and we'll take the square root of that, would be equal to the distance to the nearby galaxy, so that's d sub g, I don't know that, divided by 1,000 parsecs. Now we've got the square root of 106 over 1, which essentially, go over here to the calculator, is just the square root, second function, square root, of just 106. 106 divided by 1, but I don't need to divide by 1 because it's the same answer. And so I get that equal to 10.3 is equal to, that's like 10.3 over 1, watch how that will be solved, is equal to d sub g over 1,000. Now what I can do is I can cross multiply, and so I can say 1,000 times 10.3 is equal to d sub g. Okay? Well, times 1. Well, that's just it. So I'll just take a 10.3, so 10.3 times 1,000. And that makes it 10,300 parsecs. It's not too hard, is it? We just look for these particular thing called the Cepheid variables, or the Cepheid stars in a particular galaxy, and we use this equation. The reason it's square rooted, because it's related to the inverse square law, and when you're trying to solve something, inverse square, square root, they kind of work together. Okay, well, let's learn some more stuff. All right, actually, let me put my calculator away because we don't need it for right now. All right, we will now learn what's called the Hubble Law. So there's a guy named Edwin Hubble. Well, let's talk about him later, actually right here. But in 1911, it was discovered that all galaxies, with a few exceptions, were moving away from the Milky Way. All galaxies moving away? That's weird. Does that make us at the center of the solar system or the universe? Maybe. Well, maybe not. We'll talk about that. Edwin Hubble found that there were these speeds calculated by the Doppler ship always analysis, and he called this recessional velocity. So he discovered that all galaxies are moving away from the Milky Way. So he did the math of how far they were away, and then he used the Doppler shift, and he figured the whole thing out, and he said, huh, they're all moving away. And then he decided to plot a graph of distance in now megaparsecs, or hundreds of thousands of parsecs, versus how fast they are. And it seemed interesting that the ones that were the furthest away, like 150 megaparsecs up here, these galaxies out here were moving faster away than the ones that were closer. So then they began to figure that out. Okay, and then from a plot of several galaxies known recessional velocities, V stands for velocities and distances, in 1920 he discovered a very, very simple formula, that the velocity, okay, the velocity of the galaxies away from us is equal to some constant h times their distance. You see, basically this line, if you're a good algebra student, is a straight line. And it would have the equation y equals mx plus b. And m is the slope of the line. Well, the slope of line is, well, it's h. And he actually, the b, since it comes at 0, b is equal to 0, so y equals mx, essentially. Or he's saying v equals hd. You see, it's the same equation. And we'll talk about what the Hubble constant is. And the d is the distance. And he called h the Hubble constant, which is the slope of the line. Okay? So a little algebra there that you probably learned before. If you haven't, you're learning it right now. Although not completely agreed upon, h is about 72 kilometers per second per megaparsec. All right, so that's what that is. So it's 72. Now these right here are just the units on that. Like, you know, if I'm traveling at 5 miles per hour, the units are miles per hour. So that's the unit. So that is considered the Hubble constant. It's not exactly, like we say, completely agreed upon, but it's a neighborhood of that. All right, with h known, we can turn this around and determine a galaxy's distance by measuring its recessional velocity. So there's another way to measure how far a galaxy is. What you can do is you could look at its redshift, which we've talked about, right? If I have the spectrum of a particular galaxy, let's say this is the spectrum of a star in the Milky Way, and then what I do is I take a look at one from a galaxy that's further away, and these lines right here are just off just a skosh. Okay, these right here don't match up. Just they're off a little bit. This difference right here, the difference between here and here, is the redshift. And once you've done that, you can figure out how far a galaxy is away. So there's two ways to do that: the Cephid variable, which is the first way, and then the second way is by the redshift. Okay. So two useful methods help us to figure out. You know, I'm not sure we need to know this. Well, you can see the calculator showing, so that would mean you need to get your calculator out. Let's do another problem. How far is a galaxy? Now we're going to use the method, the Hubble's Law method, and so let's see if we can figure this one out. So a galaxy has a recession velocity of 13,000 kilometers per second. What is the distance in megaparsecs? Well, the equation we're going to use, of course, is v is equal to h times d. Now we're trying to solve for d. V is easy to determine. So what is v? Or, yeah, that's based on the redshift. So that's 13,000 kilometers per second. Now h is the Hubble constant, and if you recall, that was essentially 72 kilometers per second per megaparsec. Or let's just say h is, well, 72. That's pretty easy, right? Okay. So I can now plug in my equation. Actually, what I want to do is I'm going to solve for d first. I think I'll do it algebraically. If I take this equation and I divide both sides by h, the h cancels, and I get d is equal to v over h. So v is 13,000 kilometers per second. And h is 72. Now, actually, while let's put the units on there, and I'll show you something pretty cool. Kilometers per second per megaparsec. So kilometers per second per megaparsec. Okay, now what if you notice here? You see kilometers on top and bottom in seconds, and what do you get? You get the division of megaparsecs. So you're going to get megaparsecs. So I'm going to get in my calculator. I'm going to say 13,000 divided by 72. This is not too hard, is it? That was easy. And you get 180 megaparsecs.